We have binomial expansion to do in this question because we're told we've got 1 plus kx to the n, and we got told we need an expansion, and we're interested in the coefficients of x squared, and x to the 4. So it is worth learning the following one, the fact that 1 plus x to the n, this is n could be sort of it could be a fraction or negative or anything, is 1 plus nx plus n minus 1 over 2 factorial x squared, and you just keep going, and you keep, let me put one more in, you then have to do n minus 2, 3 factorial x cubed, plus so on. Try and learn that, because yeah, that's essential for this question, because then you can just extend it. If it's 1 plus kx to the n, it's the same thing, but you just have to replace all your x's by kx. So here goes, it's going to be 1 plus n times kx plus n minus 1 over 2. 2 factorial is just 2, so I can just write it like that now. And then kx squared Okay, just keep following this pattern, and kx to the 4, and that's enough. It does go on more than that. So we're then told that the coefficients of x squared, and x to the 4 form a geometric sequence. So here goes. This is the coefficient of x. It's a series technically. A series is when you're adding them. I'm just going to write it as a sequence. So I'm going to get nk, and the coefficient of x squared is going to be this part. K squared I get, so when I expand this out I get k squared x squared. So I just get this k squared as the coefficient, and then finally now I'm going to expand that 4 factorial out. It's going to be 4 times 3, which is 12, times 2, 24. And we're on our way now to be able to find this relationship between n and k, because the piece of information we've not yet used is that this is a geometric sequence. So each time I'm timesing by a common ratio. Now if you have something like 3, 6, 12, you can see the common ratio is 2 just by looking at it. I'm timesing by 2 every time. But how could you get that if you couldn't just see it? It's not as easy to see it here. Well, you could have done 6 divided by 3 or 12 divided by 6. In both cases we get 2. And we can do the same thing here then. We can take the second term and divide it by the first term, and that must be the common ratio. I'm also going to bring the k squared up into the numerator rather than have it outside. And then I'm dividing by nk. And that is the common ratio, but that will equal the third term divided by the second term. Okay, now it's possible. I mean, this doesn't look that nice. It's fractions divided by fractions in some cases. It's possible to start cancelling out. I'm just going to take an extra step before, and I'll show you how you could cancel it out, but just to not rush it. So I've got a fraction divided by another fraction. Well, you can keep change flip. You can take this first bit, n minus 1 k squared over 2, and you can times it instead by 1 over nk. And when you do that, nothing happens to the top, but we get the nk on the bottom. And over here, I've got n and all this other stuff. Okay, and now instead of dividing by this, I would times by the reciprocal, flip it. So I times by 2 over n minus 1 k squared. So we're going to get a 2 here, and then the n minus 1 k squared ends up here. Now we can start cancelling. So n's are going to cancel, the n minus 1's are going to cancel, the k squared is going to partially cancel, and the 2 is going to cancel to 24 to leave 12. Note, I could have done that here. Okay, it's just sort of a little bit less clear to see, arguably. And that 2 and the 24, so maybe that's the hardest bit to see. But yeah, we get the same thing. And on the left-hand side, the n's cancel, and that k is going to cancel with that. Again, I could have done this. So before I do any more cancelling, because there is a bit more, I'm just going to write it out again. Now this k will cancel partially with that, and we're nearly there now. I want to make k the subject. So let's just try and remember where we're trying to get to. This, and you can actually see a lot of the terms in there. You can see n minus 1, n minus 2, and n minus 3, and actually when we times by the 12, it's going to cancel the 2 to leave 6. So this is brilliant. K will equal 12 n minus 1 over 2 n minus 2, n minus 3, which is 6 as required. Okay, nice job. Quite a bit of algebraic manipulation and so on, but we've got to the answer. In part B, we're given some information, extra information, that n and k are positive integers, and we're asked to find all possible pairs of values for n and k and show when we found all possible pairs of values. Now note, we were told at the start of the question that n is greater or equal to 4, so that would be a good starting point. We've got this formula. Let's try n equals 4, see if we can get a value. We're going to get that k is 6 times 3 over 2 times 1. That's 18 over 2, that's 9. So that one will work. N equals 5. Okay, the 3 times 2 cancels with the 6 and we get 4. So that one also works. That's going to give me 30, and I can see that they're not going to go into 5, so this time it's not going to work. 30 over 12, that's going to be 15 over 6. No. Okay, 4 goes to both of these, it's going to be 9 over 5. Now notice it seems to be getting smaller every time. This makes sense actually because the bottom term is a quadratic. It's going to increase faster than the top term. And actually we're already less than 2, so the only real question left is if we can get k equal to 1. So as I'm getting closer, I'm just going to keep trying them. Okay, very close to 1 now. And this is actually 54 over 56, which is less than 1. So no other solutions. K less than 1 for n bigger or equal to 10. Denominator is a quadratic. Numerator is linear. Now I feel like that's enough. Just going to show you the mark scheme 1 second. They looked at where k is less than 1 and obtained a formula like substituting it sort of into here. This is less than 1, so you can create an inequality and get this. And they looked at kind of what that curve would look like. There must be a root between 9 and 10. And this is convincing because here it's going to keep increasing. I feel like mine is as convincing as that. I haven't drawn a graph, but you might prefer that. Another way I did explain it when I did it myself, actually, as I said, there can be no other pairs. Just look back at this. There can be no other pairs since neither n-2 or n-3 will be factors of 6 for n greater than 9, and they won't be factors of n-1 either. So I feel like that one's okay as well. There we have it. That's my explanation for part B. Let's keep going. Part C now, and then we've got part D. So for the case where k is 1.4, find the value of the positive integer n. Well, notice 1.4 is actually 14 over 10 or 7 over 5. And I recall that we already found 7 over 5. Here it is. So actually, I don't think we need to do anything else. From above, when k equals 1.4, n is equal to 8. And let's say you didn't spot that, or you wanted to show more working, or you hadn't done that original calculation. Well, we can still work it out, so I will show you how to do that. We can take that formula that we had between k and n, and now we can replace k by 1.4, or 7 over 5. So now I can cross multiply. I'm going to get 7, n-2, n-3. I'm also going to expand that out. Equals 30, n-1. Okay, and I've got a quadratic equation to deal with. So we expect this to factorize. And now we just need to try some values. Well, 12 and 6 are one possibility to give 72, but we won't get an odd number here then, so we don't actually need to try them, nor do we need to try 6 and 12. I've written them down. That leaves 8 and 9, or 9 and 8. 7 times 9 is 63. There's no way we're going to get 60 minus 65 there, so I can cross that one off. So for this one, I'm going to get 7n times 8 would give me 56n, and then 9 times n would give me 9n. I need them actually both to be negative, so that will work. If I add that, I'll get 65. So if I do minus 8 here and minus 9 here, then I factorized it. And n would equal 9/7 or 8. It's quite a lot more effort to get that, but I showed, that's how you could do it, and that's how you could do it for a different value of k, for example. We just need to reject that. So we take the 8. Okay, good. Let's take a look at this very last bit of this question. It just turns things to a slightly different direction. Okay. So we're told that k is now 1.4 again, as we had before, and n is a positive number, and we've just shown that n is equal to 8. And the first term of the geometric series is the coefficient of x. Okay, remember before we had, sorry, it's all the way back up here, but that was our nk. So it's not just a term in the sequence or series, it's actually the first term. So we've got nk, and then the second term was, I've already forgotten. It was n minus 1 over 2 k squared. We're asked, okay, it's a series. I'll write it as a series now. And we're interested in how many terms we need for the sum to exceed this number here, 1.12 times 10 to the 12. All right, first things first, let's work out what r is equal to. We've got, actually, let's also work out what a is equal to. So a, the first term, is going to be 8 times 1.4. So that's going to be 8 plus 3.2. It's going to be 11.2. And then r, it's going to be these two divided. So this k cancels, this n cancels. And it's going to be 7 times 1.4 over 2, which is the same as 7 times 0.7, which is 4.9. So it's going to be 11.2 plus 11.2 times 4.9 plus 11.2 times 4.9 squared, and so on. Actually, but we're interested in the nth term, so it's going to be 11.2 times 4.9 to the n minus 1, and we're interested in where that is greater than 1.12 times 10 to the 12. So we can use our knowledge of a geometric series. It's how it sums. It's going to be Sn is equal to A. Now, because the r is greater than 1, I'm going to write it this way around. It's going to be r to the n minus 1 over r minus 1. You can swap it around if you like, but this is going to be more useful. That will equal 11.2 0.2, 4.9 to the n minus 1 all over 3.9. And this is greater than 1.12 times 10 to the 12. Remember, like now we've got an equation just in terms of n. Sorry, an inequality just in terms of n, which we need to solve. Okay. Just need to remind. We've got log, got this here and this here. I'm just going to bring this down. Okay, first thing, I've got 1.12 here, and I've got 11.2 here. So I could write this as 11.2 times 10 to the 11. Out of standard form, but in a more useful form because now these cancel. And that leaves me with 4.9 to the n minus 1 is greater than 3.9 times 10 to the 11. So this means 4.9 to the n is greater than 3.9 times 10 to the 11 plus 1. Now this, because this is such a big number, this is actually, we can ignore the plus 1. This is approximately 3.9 times 10 to the 11. So approximately 4.9 to the n is bigger than 3.9 times 10 to 11. All right, I'm ready to take some logs. I've had enough. We're told these two here. We can also, maybe before I take logs, I just need to say this. So it's actually going to be 5 to the n is going to be bigger than 4 times 10 to the 11. So now I can use these two. Log to base 10 of 5 to the n is going to be bigger than log to base 10 4. Again, this is all approximate, but we're okay. And that means n log 5, remember that's typically, when you write log 5 you mean base 10, is going to be bigger than log 4 plus, I'm just doing my rules of logs for timesing these two, so it's log 4 plus log 10 to the 11. And with 10 to the 11 you can bring the 11 down like this. So 0.7 n is greater than 0.6. Now remember, log 10 to base 10 is actually just 1, so this is 11. So n is bigger than 11.6 divided by 0.7, or 116 over 7. Sevens into 11 go 1, remainder 4. 7s into 46 go 6. Remainder 4. We hope that these simplifications haven't, mess things up. So require approximately n bigger than 16. So n equals 17 is the smallest number of terms. How many terms required? Okay, quite a lot in this question has got to be said. That last bit I think is quite tough, but I hope you're happy with it. Well done.